So at first, I didn't understand this arc standard transition-based algorithm. At least, I didn't know or understand how it works by watching our video. So I looked into a little other or additional materials, and I just searched for like transition-based dependence parsing tutorial, and then this one is the first thing that came up. And then it shows a little bit better examples. So it's like kind of an action-based kind of thing. So in this dependency parsing, we have three possible action kind of choices, right? The first one is a push or a shift, and then the second one is a left arc and the right arc. Okay, so I have no idea what that means, but for these three actions, let's just look at the example. So it's a little bit more interesting example. So we start with the empty stack and the buffer, and then we can always push the item on the buffer, starting from the leftmost item, and then put it or push it into our stack on the left, right? And then as you know about the property or characteristic of a stack, we take out the top one, right? So the most recent one that we pushed, that will be the first one that we will take out, right? Okay, but anyways, so this SH is a acronym for shift, and so starting with the empty stack, we keep pushing it or shifting it, right? And then at least two of them are put into our stack. And in that case, at this moment, we have three different choices of keep pushing it or keep doing the shifting by getting one item from the buffer and putting it into our stack. And also there are two other options, which is we look at the two topmost item in our stack. Okay, so stack is like LIFO, last in first out, right? So these two are the most recent one that we put or push it or add it into the stack. And so we always look at these two entries, that are on the top of the stack. So this is a top and this is a bottom, right? And this is an oldest one, and then this is the newest one. Okay. Okay, so we only look at these two and then determine whether we have to assign the dependency like this or this. Okay, so these two are the two other options that we perform in this case. Okay. Okay, so in this case, it is having a dependency like this one. So this LA means left arc. So we draw or assign this left arc. Okay. Okay, and then after doing this this action, we do one more thing. So from here, this child node. So this child node will get removed. Okay. So that way, after we assign this left arc relationship or dependency between these two, and then we remove this target one, because that was assigned as a child node of some parent node. Okay. Okay, and then we have only one entry here. And then if you want to obtain this article, or this tutorial, as I mentioned, transition based tutorial. I think it is this one. Hopefully, let me check. Yeah, okay. So this one is the one that we are looking at. Okay. Transition-based dependency parsing tutorial. Okay, and then we only have one entry here, and then we keep pushing it. So we add one item or move one item from buffer to stack. Okay, so in this case, we check whether we have to assign this or this. But yeah, we decide not to assign any of these two relationships, right? And so the next thing is to keep pushing. So pushing it, and then, so here, let's see. Okay, so in this case, this kind of relationship is also, assigned. Yeah, I'm not very familiar with the why. Yeah, I don't think it's that much intuitive, but this seems to be some rule in terms of a dependency parsing. So this is a kind of modifier, and this is the one, target one that gets modified, right? So in this case, this is a kind of root node, and then this is a, this is a parent node, and this is child node. Yeah, so that seems to be the rule used in the dependency parsing. So in this case, we assign this left arc. Okay, so we assign this, and then we remove this child node as well. Okay, and then we get those two entries remaining, and then we keep pushing another item. Okay, and then from here, we have no more item here, and then we determine whether to assign a right or a left arc in this case. Okay, and here in this case, we assign this right arc, and then this one is the one that we have to remove, right? So we remove it by assigning this this arc, and then we get these two, and then this guy is the one that we have to assign at last, right? So that way, so previously we handled all these adjacent words that are just placed to near each other, but after removing some of them selectively, and then we are able to assign these remotely located keywords and their dependencies. Okay, so this is how it works. Okay, and then in this case, how we formulate this as a machine learning problem is, so we describe this kind of particular situation as a feature vector. Okay, so what is the rightmost one, the topmost one, and the second topmost one, and so on. And maybe we can use some history information, right? So this is basically a sequence of 3 different actions in order to assign different dependency parsing results, right? So in this case, it's definitely a sequence of these different assignments or different action choices. So in this case, our feature can also involve or contain the previous actions as well. So what we did in the previous time step or one time step before that. Okay, so that could be also included in our feature vector. So once we construct some feature vector that describes this situation, like including the what we did in the previous 2 time steps. I mean, that's just one example of building up or constructing the feature vector, and then we describe we extract out some other features that describes the current situation. For example, like word ID or index of the topmost one, and then maybe some POS tagging information, because the POS tagging is also determined before running this dependency parsing, right? So the lecture said that we first run the POS tagging and then assign those tagging information, grammatical tagging information into each of our words, and that is also another features to include in our feature vector. Okay, so so based on the feature vector, it's just formulated as a multi-class classification problem that has 3 different categories, right? So that's how we run or formulate this dependency parsing as a machine learning problem. And then here, in this example, so we have this kind of particular type of a dependence arc, particular type of an arc. So it's not just a left arc, but this left arc should be a particular type of determinant relationship. So it's like, maybe article and some noun, that kind of relationship is described by this particular type of an arc. Okay, so in this case, it was called the let's see. So if you remember, this kind of accuracy comparison. So it was about like neural net based dependency parser that this Chris Manning have built or proposed. But what was the difference between these two? What was the difference? Yeah, right. Yeah, right. So it's unlabeled, and this is labeled, right? So in this case, this is basically a labeled case that determines the particular type of this arc, right? So in that case, the left arc can be categorized into maybe 15 different types of relationship, like determinant or maybe some subject-object relationship and so on. In that case, our left and the right arc can have a multiple different types, and so in that case, the total number of categories that we have to classify among will be maybe 30 different classes, and then the multi-class classification problem should deal with these much more number of different classes. So that is the difference between these two. Yep. So that was a brief overview about how the dependence parsing works. Okay, so any other questions? I didn't prepare much to explain in more detail from my side, so I see if you have any questions in this chapter. 질문 뭐 없어요?
다음 슬라이드에 인풋 피처 만드는 툴 자리
만드는 사실 나도 잘 모르는데 계속 모른다고만 얘기하는데. Okay, so this is about let's see. Good has control. Good. Okay, I think it's yeah, describing the feature vector or the constructing the feature vector to describe or characterize this particular situation. So since you guys know how the like transition-based dependency parsing works, so suppose this one is like our current situation, and then yeah, so this is a kind of a blank or dummy node, which is a kind of a root node, and so this is a topmost one, and then this is a second topmost one, yeah, contained in our stack, or yeah, right, and then this one is the buffer one. So it looks like yeah, the word first describing the keyword that was placed in the topmost one, secondmost one, until we hit the root node, which is kind of a dummy node in our stack, and then this guy seems to be our buffer, yeah, buffer keyword in this case. And in that case, suppose our vocabulary size is 500. So in total, yeah, we have a 500 unique keywords, and then this one will be like 500 keywords. I mean 500 dimensional one-hot vector, and then this one will also be another vector, and then another vector, and so on, right? Okay, and then so given these vectors, we start, yeah, we also concatenate other additional information into our feature vector. So this is a POS tagging associated or attached attached to our keywords, right? So for each keyword, so we already got assigned for this POS tagging information, right? And then suppose we have maybe 15 unique POS tagging type. So this is like different kinds of POS tagging, like JJ and VBC and some other POS tagging. And in total, they have a 15 different types. And then we can represent this guy as another 15 dimensional one-hot vector, and then another one, and so on. Okay, and then we can also concatenate those feature vectors into these one-hot vectors obtained from each keyword in I mean, yeah, each keyword for its POS tagging information. And then in this particular case, yeah, we will have 3 different 15-dimensional vector, and also if it is a empty one, okay, in this case, yeah, in order to describe this situation, we are considering the previous history or the previously assigned dependency parsing information. Yeah, so in this case, once we reach all the keywords in our vocabulary, and then we start with these previously assigned dependency parsing information about this S1, whether it has a left arc or right arc. So if it has 0, and then it's just a 0 vector, and then also it's like a 500 dimensional vector that maybe has a 0 vector. I mean, it may be wrong, but yeah, it's kind of conceptual, kind of hypothetical description about how we construct a feature vector, which is basically concatenation of all these information. Okay, and then for the second one, it is already assigned for this left arc corresponding to this keyword he, and then that is also another feature vector represented as this 500 dimensional vector. Okay. Yeah, and then this one is this particular left type of this left arc kind of a dependency that we assign. So yeah, basically we just concatenate all these feature vectors, which is really large sized vector. Okay, but in the case of neural net, we just represent each keyword by using a word embedding, and also for each POS tagging type, we also represent it as a word embedding vector as well, right? So that way, yeah, we use much smaller number of dimensional representations for each keyword, and also the POS tagging, and then also dependency like type, and then we just perform the neural net. Okay, so all these dense versions of a feature vector will be concatenated into this form, and then we run this two-layer neural net in order to obtain the action that we have to perform at the particular moment, at this moment. And also, yeah, before using a neural net, so as you can see, this one is really large. Large-sized vector. The dimension could be ridiculously high, right? So in this case, of course, we do not represent it as a kind of dense vector. Of course, we use a sparse representation, right? Sparse representation, and then also, and also our yeah, and also our machine learning model will actually assign some linear kind of weight for each of these each of these dimensions. So we may study some other NLP tasks called the NER, named entity recognition. Yeah, also I haven't studied it in much detail, but one representative algorithm to perform this named entity recognition. So what is named entity recognition? It's just detecting some phrase corresponding to either person name, like Michael Jordan, did something, and then we have to detect Michael Jordan as a single phrase corresponding to a person type. So named entity means those kind of unique entities in a particular type, and that is either like person name and then the location, maybe New York Square, and also it could be like New York Times as well, like a newspaper kind of company, and also what other types do we have in the named entity recognition? Location, person name. Organization, right? Like company name, WHO or something. What about the date? Is it considered as a named entity or not? Like April 23rd, 2017. Is it considered as a named entity? So I'm asking if because I don't know. So 이것도 돼요? 이것도 named entity로 recognize가 되나요? 잘 아는 사람 없어요? 혹시? 뭐 인디펜던스 데이 뭐 이런 거요? 뭐 뉴 이어스 데이 뭐 이런 거. 근데 이제 특정 날짜는 아니고 그쵸? 메이 the 3rd 뭐 이런 건 아니고요. Okay, anyways, yeah, that is the name density recognition. And then so yeah, one representative algorithm to solve or handle this name density recognition was CRF, which is a conditional random field. And then this one is quite similar to hidden Markov model. Yeah, but anyways, that's like a sequence-based model. But if you study this CRF or this kind of NER type task, and then it exactly uses this kind of really large-sized vector and but very sparse version of the input vector. Okay, so in that case, all the features are considered as a kind of binary features. So the feature is either 0 or 1. So in this case, so there is no like real valued or categorical kind of valued feature variable, right? So in this case, it's all either 0 or 1, right? So in this case, given your feature vector, suppose this one is 1 and this one is 1, and then we are basically learning this NER for, learning this conditional random field for the task of an NER. So it's equivalent to like learning the linear combination weight for each of these features. In case it is a 1. Okay, so in that case, it's kind of so if we think of the linear combination of all the different features, and then it's like the total sum before maybe doing the softmax or maybe sigmoid or whatever. So those can be represented as the linear combination of these those learned weight. Okay, learned weight only for the features that are turned on. Okay, so in this case, it's all binary features, so we can understand it as being turned on or off. Okay, and then also in this lecture, so we often really increase the number of features in a really crazy manner. So previously we already had so many like dimensional features, but also we can think of this composite kind of features. So when those two features are turned on, and then we define it as a additional new feature. So in that case, so that will take up another new dimension, and then we will assign a new linear combination weight for that feature. So in that case, those two features are both turned on, and then we have like a additional kind of feature, and that way these kind of composite features of multiple original features will also will also have quite a lot of numbers, a lot of different features, right, that we can create. So we just add all these features into our machine learning framework like this CRF. Okay, so that way we kind of we want to kind of overcome the linearity of our classifier. So in this case, so as I mentioned, so once we fixed this weight like 0.3 and 0.4, and then altogether, if it's both turned on, and then the probability, let's consider it's a binary classification, like whether it's a named entity, word contained in the named entity or not. Okay, so let's just simplify it as it's a binary classification, and then it is only giving like a 0.7, and then in the sigmoid function, 0.7 will not have a much probability. But in this case, if it is both turned on, and then let's define another new feature where if those are both turned on, and then this one is also turned on, right? And then in this case, we can assign a new kind of weight, linear combination weight on this feature, and thus, in this case, even if they are both turned on, we cannot just we can just have only the summation of these two values. right? So that's the best that we can do. But if we have this feature, and then if we assign this one as maybe 10, for example, and then we can really boost up the score when these two features are turned on, right? So it's like yeah, some word was like appearing after like in, and then also it is starting with the capital letters. So we can of course define that kind of feature, in order to binary classify this word in terms of whether it's a named entity or not, right? So in this case, yeah. So it is after in or after maybe preposition, and then it's starting with the preposition. Yeah, after the preposition, and then it's starting with the capital letter, and then like this one is like yeah, when both are true, and then by assigning this as a like a big probability, and then yeah, we can kind of yeah, overcome the linearity of our classifier by just doing the linear combination of the individual features that we defined. Okay, so this one is kind of a typical setting for this kind of NRF, conditional random field or any other, yeah, before deep learning era. So this was kind of a quite typical kind of practice when running the machine learning algorithms for this kind of complicated tasks. Yeah, by just extracting out all the possible atomic features, very small kind of feature, but we extract out so many different features, and that way dimension can be really high. But yeah, modern, yeah, but yeah, state-of-the-art machine learning algorithms can handle these with no problem. Like a CRF or like tree-based method, yeah, they will have no problem in being, yeah, I mean, in terms of a scalability with respect to this number of dimensions of our data. Any other questions?
프로젝티브랑 논 프로젝티브가 좀 헷갈리는데 크로싱 되는 거 여부를 따지는
그런 거 같아요. 아니에요.
그거에 대한 설명 잘 안 되는 것 같아요.
나도 마찬가지예요. 나도 뭔가 설명이 부족해서. 매닝은 연구도 잘하고 책도 잘 쓰는데. 네, 그 약간 관련하고 나는 이게 좀 그런 좀 펀더멘털하게 이게 아까의 그 트랜지션 베이스드의 디펜던시 파싱을 가지고 그런 알고리즘을 가지고 우리가 예를 들면 얼기설기 있는 그런 디펜던시 파싱의 결과를 싹 다 나타낼 수가 있는 거냐. 그러니까 우리가 매번 옳은 판단을 100% 다 한다 하더라도 트랜지션 베이스드라는 게 기본적으로 이렇게 뭐 계속 이렇게 넣어갖고 이렇게 해갖고 할당하고 빼고 그러면 또 먼 디펜던시 같은 경우는 이게 빠지면서 생기는 거거든요. 그렇잖아요. 그러니까 우리는 항상 그 스택에서 이렇게 두 개만 딱 보는 거죠. 그러니까 먼 디펜던시는 걔가 빠져야 돼요. 걔가 먼저. 그죠? 걔네들이 어떻게 보면 디펜던시 파싱이 좀 차일드 노드처럼 가장 밑단에 있는 어떤 그 어제이슨트한 그런 놈들을 우리가 먼저 처리를 하고 조금 한 단계 올라가서 예를 들면 징검다리가 가운데 하나 낀 놈, 뭐 그런 놈들도 처리하고 또 이렇게 걔들 좀 빠지고 또 먼 애들 남은 애들 중에서 또 이렇게 좀 이어주고 약간 이런 건데 저렇게 이렇게 쭉 가는 것만으로 모든 종류의 트리를 다 만들 수는 없을 거라고 생각이 들고, 근데 그게 뭔가 프로젝티브는 만들 수 있고 이론적으로 프로젝티브가 아닌 거는 만들 수 없고 뭔가 그런 건 아닐까 그런 생각이 들어요. 그렇잖아요. 저걸로 표현을 못하는 어떤 디펜던시 파싱 구조도 또 있을 수 있으니까. 네, 하여튼 그런 생각이 좀 들었어요. Okay, so yeah, so the issue was so whether by using this transition-based one, which keeps pushing our words from right to our stack on the left, right? So the question is like whether it is possible to represent all the various different dependence parsing results or not, right? So in principle, I don't think it can represent all the possible kind of dependency relationships, but yeah, my conjecture is. In the case of this kind of simple, in this case of a projective one that doesn't cross, where the edges don't cross with each other. In this case, it may be represented by the transition based or like kind of simple kind of transition based dependency parsing kind of algorithm. But yeah, I'm not sure. Yeah, and also this Chris Manning also mentioned about the scalability or the efficiency of this transition-based dependency parsing. So in this case, so we can just do this dependency parsing by just touching every keyword just only once, right? So there is no going back. Like, so if we add one word from our buffer into the stack, and then there is no way going back, like popping one item from our stack and then put it back into our buffer. So there is no such cases. So that way it's like the scale scales linearly with respect to the number of keywords, right? So we just passes or touches just only one time for each word, and that is that way we can just obtain the final kind of dependence parsing result, right? So that is one kind of beauty or advantage of using this transition based dependency parsing algorithm. 또 다른 질문 있나요? Any other questions?
영어 같은 경우는 여기서 이밸류에이션의 그 셋으로 프로필 뱅크를 얘기했는데 다른 언어 같은 경우는 혹시 이밸류에이션을 어떤 기준으로 하는지 되게 쓰시면
뭐 있어야지 일단 하겠죠. 근데 뭐 모르겠어요. 우리나라 한글도 있나? 한글 혹시 해본 사람 있나요? 한글 디펜던시 파싱? 여기는 뭔가 NLP를 다들 배우러 온 사람들이지 전공하는 사람들은 아닌가요? 나도 배우러 왔는데 어쨌건 뭐 하여튼 그라운드 트루스가 없으면 이거를 뭐 평가를 뭐 못하는 거는 뭐 당연히 맞겠죠. 그 무슨 유니버설 어쩌고 거기 웹사이트에 보면 뭐가 쫙 그 언어별로 뭔가 나와 있는 것 같은데 여기에 보면 무슨 뭐가 있지 않았나요? 네, 이거 뭐 유니버설 나도 이거 들어가 보지도 않았는데 여기 보면 뭐 언어. So this website seems to contain dependency parsing result on the different languages. Of course, we can find the Korean here. So we may want to check this website to see if there is a ground truth dependence parsing information on other languages. It looks like Koreans also have some ground truth on the dependence parsing. But yeah. Any other questions? Okay, then. Yeah, let's finish this chapter. Yeah, and then maybe let's have a break a little earlier than usual. And then we start, we resume at 3:06. Okay.
렉시컬 아이템이라는 게 있잖아요. 단어와 단어 사이 그러면 A가 반사잖아. 그게 디터미너거든. 그게 그러면은 그치. 그러니까 그러면은 그 디터미너는 그 나온 프레이즈에 나온 문제에 의존을 하는 거지. 그러니까 뭐 보면 그게 앞에 얘는 언어학적인 얘기야. 그렇게 해서 언어학적 반대로 그냥 이 문장을 분석을 하는 거지. 어떠한 예시가 되는 사이에 관계가 있고 소리가 만들어지는지 보려고 실기를 넣고 그냥 틀렸는데 지금 이걸로 기계가
한명꼴로 그런 경우가 있다면서 레인이 나는 거라고.
진짜? 그러면 우리 오피실에는 2명 있는 거야. 아니 그 오빠 진짜 그러면
나 보냈어. 이게 잡아 2, 3일 걸려.
안 좋은 나올까봐.
자, 이쪽 거의 하루 걸려서.
이런 거 관련해서 지금 이런 거 되게 많이 PR 이거 들어왔어. 얘기했던 게 이거 어떤
한번 해줘야지.
공모시 없더라고.
내가 내 거울을 봐도 사실 모습을 살짝 소름이 끼치고 목을 대체 무슨 힌트를 사랑하는 머리부터 발끝까지 힌트를 쫙 바르는 거야. 모든 거울을 봤으니까 소름이 끼치는데 공됐으니까 이거 줘야 되는 세트를 하는 거야. 키스 맞죠? 내시경 재검사
나는 같이가 안 와서
NER 같은 거 할 때도 그러니까 네임 덴시티 레코그니션 할 때도 아마 저게 저런 정보가 있으면 그러니까 뭐가 한 덩어리의 명사 구인지를 좀 알 수가 있잖아요. 네, 그러니까 뭐 뉴욕 타임즈 같은 경우는 아마 타임즈에서 뭐 욕으로 가고 아마 욕에서 뉴로 가나 이렇잖아요. 뭐 이렇게 디펜던스 파싱을 생각해보면 그러면 그게 한 프레이즈로 일단은 이 디펜던스 파싱에서 잡히니까 그러니까 그런 정보를 그 이후에 그러니까 저거만 해갖고 뭐 저거 갖고 뭐 하느냐 어떤 엔드 태스크로서 저게 이렇게 중요한 의미를 가진다기보다는 저런 정보들을 저기 어떤 워드 인베딩처럼 워드를 나타내는 어떤 부가적인 정보로서 또 사용을 해서 뭔가 하는 경우도 많이 있고요.
그러면 저기서 워드 인베딩 들어가잖아요. 워드 인베딩 할 때 그 인베딩 메커니즘은 이미 스킵프레임이나 게노바에로 이미 다 학습을 시킨 걸로 가지고
네, 보통은 그렇죠. 네. 파인 튜닝을 뭐 하는 경우가 많이 없죠.
POS 태그가 아쿠 레벨 인베딩 메커니즘은 어떻게 학습을 시키거든요. 다른 모델에서
따로 돌린 다음에 이쪽으로 이제 가지고 오는 거죠. 이게 뭐랑 연결이 돼 있다라는 거. 그러니까 POS 태깅 같은 경우는 그냥 원합 벡터로 넣어주거나 POS 태깅 그 저희 각각의 품사들을 이제 그 원합 벡터로 넣어주거나 아니면 아까처럼 그 인베딩 벡터, 댄스 벡터로 이렇게 만들어 놓은 게 있으면 이제 그거를 컨캣을 해주는 거예요. 워드 인베딩 벡터에다가 그러면 그 품사 정보까지 이제 포함이 이렇게 우리가 입력으로 주는 거죠. 뭔가 센티멘트 어널리시스도 뭔가 할 때. 그래서 뭐 예를 들면 뭐 예. 이거 같은 경우에 이게 이런 뭐 니게이션 같은 거 좀 핸들링 할 때 이게 그러니까 the film doesn't care about 어쩌고 이쪽은 아마 다 좋은 얘기인데 doesn't care가 되니까 이게 최종적으로 나쁜 얘기가 되는 거거든요.
그러니까 이 작업, 이 트리를 만드는 거는 파싱으로 한 다음에 그 다음에 센티미터 어널리시스.
네, 그렇게도 하고 근데 이거는 그냥 이거를 한꺼번에 하도록 했어요. 저
파싱이랑 센티멘트가 그 엔드 투 엔드로 다 돌아갈 수 있고.
그렇게 이거도 했고 네. 뭔가 의미 단위를 좀 파악을 하기 위해서 저거를 기본적으로 좀 하는 거예요. 그러니까 여기서부터 여기까지가 한 덩어리, 또 더 크게 보면 여기서부터 여기까지가 한 덩어리 이런 것들을 뭐 정확하게 어디에 저거를 어떻게 좀 구체적으로 어떻게 쓴다는 걸 좀 잘 모르겠어요. So before moving on to the session about the leaks, any question? Any last question? Okay, then